today we're going to go ahead and talk about bank curves. So what I want you to think about, if we have a car on a highway going around a turn very, very fast, what do they oftentimes do on highways? Well, you'll notice that the highway is a little bit tilted or a little bit banked, and this allows it so that the car can turn. Think about how easy it is to turn. Like if the road is flat and there is not much friction, it's really, really hard to turn. So things like friction and banking a curve can help things so that they can move around like a circular type of motion. Cool. So we're going to go ahead and look at an example problem together. So in this example problem, the road is frictionless. Pretty crazy. In class, we'll watch some fun videos of like an example of this. It's pretty crazy what you can do with a banked curve. But let's go ahead and draw it out. So let's imagine, so we have something banked and all. So imagine this ramp coming out of the page and it's going around in a circle of radius. So we have like a little car, which they don't give us a mass for this car, so let's just call it M. And it's like moving in a circle kind of like that all the way around. So like this banked part is just continuously going around. Okay, so we know the radius is going to be 200 meters. And the car is moving at 25 meters per second. Okay, so I'll put that up here. Velocity is 25 meters per second. Okay, so we know that anytime we solve a problem involving circular motion or forces, we go ahead and draw a free body diagram. So let's think about what forces. First off, we know there's always gravity acting on things with mass. So force of gravity is going to be equal to mg. Let's think about what else. So there's no friction. This is pretty crazy. However, there is a surface pushing on the car, and that causes a normal force. So there's going to be an Fn. And I should say this angle right here is theta. And that looks like that's what we want to find. Cool. So, wow, this is pretty crazy. So now let's go ahead and do a coordinate system. Okay, so I want to think back to the beginning of the year. So at the beginning of the year, remember when we had a ball or something on a ramp and it would accelerate like up and down? In those cases, we said that the direction of the ramp is the x and perpendicular to the ramp is the y direction. And that was so that it is accelerating in the x direction, but perpendicular to it, there is no motion. The net force in the y direction is 0. So that's again if the object is accelerating up and down a ramp. Let's think about what direction the acceleration is in this case. Okay, so it's moving, it's not moving up and down at the ramp. We don't want the car to slide, but it is moving in a circle. So the direction of the acceleration is just going to be towards the center of the circle. So because of that, we are going to do a new coordinate system. We are going to say that the y direction is perpendicular to the acceleration, and the x direction is going to be like what we normally say is x direction. And I guess I should say y is like the normal one. And again, that is because it's moving in a circle, and the centripetal acceleration is pointing towards the center of the circle. Cool. So now let's think about what forces we need to split into x and y. Okay, so Fg is just in the y direction. It looks like Fn. We're going to have to split that into the x and y direction. So let's go ahead and split that into the x and y. So let's think about what angle is. So again, this is going to be Fny, and this is going to be Fnx. Let's think about what angle is what. So let me just draw like a parallel thing. Okay, so we know from the beginning of the year, this angle right here is theta, which means this is a right angle. This angle is going to be 90 minus theta. So this top angle right here is going to be theta. Cool. So we know Fny, that's on the adjacent side, is going to be Fn cosine of theta, and Fnx is going to be Fn sine of theta. Awesome. And I encourage you, prove it to yourself, give yourself a little more time. I know I kind of brushed that a little bit. I'm going to go ahead and redraw that free body diagram to the side. I know I have a lot of colors going on. So again, there's Fny is Fn cosine of theta. We know we have Fg, which is mg, and we have Fnx, which is Fn sine of theta. Okay, so let's go ahead and set up Fnetx and Fnety using this yellow where the green force is free body diagram. So Fnetx, let's think about what forces are acting in the x direction. It looks like just Fnx. That's pretty cool. Fnety, we have Fny pointing upwards positive minus Fg. Okay, go ahead, and again, you should have tried that yourself. sorry, I need to remind you to do it yourself first. But go ahead and try the rest. Think about what you can plug in for f net x, f net y, all that good stuff. Okay, so after you've thought a little bit, f net x. So it's moving in a circle in the x direction. So let's call that f net xc. So again, that is going to be MAC, which fn x we said was fn sine of theta. AC is, we know, v squared over r equals what? Fn sine of theta. Okay, our goal in the end is to find theta. This is a problem with numbers, so we should get a number. We don't know enough. We know radius and v, but we don't know m or fn. Okay, let's come back to that. Let's think about the y direction. So f net y. So it's not moving in the y direction, and it's also not moving in a circle in the y direction. So we know the net force is going to be 0. Fny we know is Fn cosine of theta minus mg. Okay, so now we have a system of equations. How can we go ahead and solve this with a system of equations? Oh, lovely. Okay, so it looks like we could have Fn, it looks like we could solve for it and plug into the other, or solve for m. Either would work. I'm going to go ahead and solve for Fn using the y. So this is what? Mg equals Fn cosine theta. Then we have what? Mg over cosine of theta equals Fn. Cool, let's go ahead and plug that in. So we have m times what? V squared over r equals mg over cosine of theta times sine of theta. So let's go ahead and do some simplifying and see if we can solve. So m's cancel out. Let's move that g to the other side. So we have v squared over rg equals sine of theta over cosine of theta. I know sine over cosine is tangent of theta. Oh my goodness, we're almost there. Cool. So now to solve for the angle, it's just going to be and again, if we want to find the angle, we're going to have to use inverse tangent of v squared over rg equals theta. So let's go ahead and plug in our numbers. So it would be what? Tangent inverse of v is what? 25 squared. Radius is 200 and g is 10. And when I plug that in, sorry, I left a mess. I got